The 2010 earthquake in Chile, a massive 8.8 magnitude event, it was a brutal reminder of the Earth's forces caused by the movement of tectonic plates along the Ring of Fire. This earthquake reinforced a key lesson. Earthquakes don't kill people, the failure of our construction does. The collapse of the Alto Rio building highlights where engineering failed. Our role as civil engineers is to step in after an earthquake to assess and assist, and to answer new structure never fail. The first challenge is structural engineering. A structure must primarily resist horizontal loads generated by seismic ground motion. To achieve resilience, we focus on two properties: stiffness to limit shaking, and ductility, the ability to undergo large non-fatal deformations, to dissipate the seismic energy. This is why we must continually improve design standards against horizontal loads. When designing in seismic areas, engineers are explicitly taught to avoid stiffness and mass irregularities and to avoid localized connections. Good seismic design is an investment, not a cost, drastically reducing potential losses. In workshop 2, we put this into practice. We constructed a model of a structure like the Alto Rio, demonstrating that the failure was not in the core elements, but often in the connections between columns and beams. The key to survival is ensuring a continuous ductile path for the seismic force from the roof to the ground. The second essential discipline is geotechnical engineering. Focusing on the ground beneath us in granular soils like sand, stability is governed by the angle of friction. However, earthquakes introduce dynamic forces that can cause catastrophic geotechnical failures. The most significant failure in Chile 2010 was liquefaction, where saturated sandy soil, due to cyclic loading, temporarily loses its strength and starts behaving like a fluid. This led to widespread damage, including the total failure of the Las Palmas tailing dam. In workshop 3, we performed a pseudostatic slope stability analysis for granular material. Our results clearly showed that as we increased the horizontal acceleration, the factor of safety against failure dropped sharply. This confirms the need for soil improvement or robust foundation in seismic zones. In summary, by integrating principles of ductility, proper structural design, and soil stabilization, we can transform an earthquake into a manageable event. Our purpose is to engineer resilience and safeguard lives.